Hello class, welcome to the next segment in lecture 26, and in this segment we're going to cover another topic that's sort of related to atmospheric chemistry, and that specifically is going to be the role that, or an overview of how exactly ultraviolet radiation from the sun influences the uh, chemical system of the Earth, for lack of a better term. So that's going to be the main subject for this segment. And to start off with, I'll go ahead and say that a lot of Earth's chemical reactions are, in fact, what's referred to as photochemical reactions. That is, some sort of reactants combined with a high energy photon of some sort to produce the products to initiate the reaction. And it turns out that ultraviolet radiation from Earth's sun is largely responsible for initiating many of Earth's chemical reactions. And we're going to take a look at a few of them. We kind of briefly mentioned this in a previous lecture, in some previous segments, and we're actually going to go ahead and take a look at them in a little bit greater depth. So one of which, and perhaps one of the most important, is the idea of photosynthesis, where carbon dioxide and water combine with a high energy photon, usually something in the ultraviolet spectrum, and then that reaction then yields oxygen, molecular oxygen, and glucose. And you might also remember seeing something like this in some biology classes, but this reaction is very much driven by a high energy photon. And again, the technical term for this reaction is referred to as a photochemical reaction, and it's called a photochemical reaction because it involves the absorption, it involves the absorption of some sort of high energy photon, which usually in the case of Earth and the Earth system is usually something that's in the ultraviolet spectrum. And another one that we've talked about as well is the idea of nitrogen oxides reacting with a high energy photon, again, usually the sun's ultraviolet radiation, to produce tropospheric ozone. And it might also be worth mentioning that I mentioned before that we like stratospheric ozone. Ideally, we want stratospheric ozone to prevent too much solar radiation, too much ultraviolet radiation from reaching the surface, which can be bad if too much ultraviolet radiation finds its way into the troposphere. But at the same time, we don't want to completely eliminate all of the ultraviolet radiation that reaches ground level, because then if you eliminate all ultraviolet radiation, then photosynthesis doesn't occur, which means plants can't grow. If they can't absorb ultraviolet radiation, then the plants can't grow at all because they can't generate the nutrients that they need in order to thrive. And one of which, and the only way they can do that is through the process of photosynthesis. And also, this comes into play in the stratosphere. So we haven't really talked about this so much, but when ozone is subjected to high levels of ultraviolet radiation, it will typically absorb it, and then ozone itself will break down into molecular oxygen and what's referred to as atomic oxygen. So molecular oxygen is just two oxygen atoms bound together to form a single molecule, and then atomic oxygen is just a standalone oxygen atom. So sometimes this is also just referred to as an oxygen atom as opposed to molecular oxygen. And usually after the reaction occurs, this right-hand side isn't exactly stable. The oxygen doesn't want to be by itself, so eventually it will just sort of rebind itself to the molecular oxygen to form ozone. So this is only a temporary breaking apart, but this is only temporarily breaking apart the ozone into oxygen, molecular oxygen, and an oxygen atom. Eventually, this right-hand side will recombine to form ozone at some point. But this absorption of ozone in the stratosphere is also one of the reasons why the stratosphere is so hot, because of all this ultraviolet radiation that's being absorbed by that ozone layer, which is the process of absorbing radiation usually generates some sort of heat energy. So all this ozone absorbing all this ultraviolet radiation is responsible for heating up a good portion of the stratosphere, and the stratosphere is also a very stable layer in the atmosphere as a consequence, because you have the relatively cool troposphere sitting beneath a layer of really warm air that is the stratosphere. So that's just sort of articulating what I just said, how the ozone absorption of ultraviolet radiation, the process of absorbing ultraviolet radiation, is largely responsible for heating the air in the stratosphere. And if we talked about one consequence of ozone being depleted in the stratosphere, and that is more ultraviolet radiation reaching the troposphere. And that can lead to all sorts of detrimental effects for the life that's on Earth, but that can also result in the production of tropospheric ozone. So if you eliminate stratospheric ozone, you let more ultraviolet radiation in to react with nitrogen oxides, which are in the troposphere. If you deplete stratospheric ozone levels, you let more ultraviolet radiation into the troposphere, which can then form tropospheric ozone. And tropospheric ozone can also absorb ultraviolet radiation. So ultimately, what can happen is if you deplete levels of stratospheric ozone, you can increase the levels in tropospheric ozone. And if you have less stratospheric ozone, you don't have as much ultraviolet radiation being absorbed in the stratosphere, which can then result in the cooling of the stratosphere because not as much of that ultraviolet radiation is being absorbed anymore by the ozone. So that means not as much heat is being generated, which means the stratosphere will tend to cool off. So that's one potential consequence of depletion of stratospheric ozone. But another consequence happens in the troposphere where you have an increase in ozone levels. If you increase the level of tropospheric ozone, then suddenly all that tropospheric ozone has the opportunity to absorb solar radiation from the sun. So that means the troposphere is going to be absorbing all of that solar radiation, which is then going to heat up the air inside the troposphere. So the ultimate end result is a stratosphere that will be cooler than what it is, say, present day, and a troposphere that will become warmer than it is present day. So it's kind of an interesting thing how if you deplete ozone levels in the stratosphere, you generate higher levels of ozone in the troposphere. Again, we don't like tropospheric ozone because ozone is not something our bodies handle very well if we start breathing it in. But the other consequence of that is you can actually heat up the air in the troposphere if you put more ozone in the troposphere. And one way you can achieve that is to allow more ultraviolet radiation to reach the troposphere to initiate this photochemical reaction that will form ozone in the troposphere. Of course, you also have, in order for this to happen, you also have to have nitrogen oxides present in the troposphere. So if that were taken out of the equation, then this wouldn't happen. But in the real atmosphere, you have all these different constituents, all these different chemicals floating around, and that also includes nitrogen oxides. But that's this is the final topic that I'm going to cover as it pertains to atmospheric chemistry. In the final segment of this lecture, we're going to actually talk a little bit about more of a specialized topic, take a look at how meteorology can influence the field of both structural engineering and urban planning and urban development. So with that, I will see you all in the final segment.